Yes, we can see your slides
Okay.
and you as well. So I'd like to welcome Professor Teruo Ono, who will be telling us about his breakthrough experiment from 2020. And it looks like a few others as well. So Professor Ono, please take it away.
Thank you very much. So I am Teruo Ono of Kyoto University, and good morning, good evening, and good night to everybody. And thank you back for having a chance to talk here. So I'm talking about superconducting diode effect in Rashba superlattices. And the reference is there. And I think I will devote a half of my time to present our unpublished results. Let me start. Okay, so the collaborators. So this is the collaborator, Institute of Chemical Research, Kyoto University. In addition to my group, we got help from the group of Professor Yuichi Shimakawa, and we got support, theoretical support from the group of Professor Yuichi Anase. Today, Akito Daido will present some theoretical work. We have also collaboration with the group in Far Eastern Federal University. And I would like to thank to all members in my group in this photo. So my group is called Nanosprint Club in Institute for Chemical Research, Kyoto University. Okay, let me start my scientific talk. So as you may know, I'm not an expert in the field of superconductivity. So let me start with my motivation. So I was very much impressed to see the first discovery of the bulk superconductor without inversion symmetry, because they show unconventional superconductivity like singular triplet pair mixing or topological superconductor or FFLO state. And because of that, people are interested in seeking this kind of superconductor without inversion symmetry, not only in bed, but also using interface or to the materials. And because I'm a field of guy in superlattice, I get the idea, why not make the superlattice, artificial superlattice ABC? Because if you make ABC superlattice by choosing elements A, B, C, then this material naturally breaks the inversion symmetry like this. And furthermore, it's well known this kind of material can give us a possibility to engineer the band structure by tuning element and thickness and the period of the superlattices. And also we know by using this kind of film, we can easily make heterostructure, and it's easy to do microfabrication. It means we can enjoy the experiment using Josephson junction or under reflection, or actually I am the field of spintronics, we can measure spintroc measurement by using this kind of material. And I believe this is a new platform for superconductivity study. That's why we started this project. So one day, I asked my student, PhD student, Yuki Endo, just choose 3 elements in this periodic table and make superlattice. And he chose vanadium, niobium, tantalum, this line, because there's some report by using niobium tantalum, we can get very good quality superlattice. And all these elements show relatively high TC like this. Then he prepared the superlattice of niobium tantalum naive vanadium tantal and on MgO substrate. So this is structure. And after fabrication, he did check the structure by using lead and X-ray diffraction. So this shows we really got the epitaxial film, and this X-ray diffraction shows the our superlattice was prepared as designed. And from this reflection, so we can see this film is growing along 001 direction. And this is difference. Okay. And so, okay, we checked superconductivity for these films. We made films ABC superlattice with different thickness, 1 nanometer, 2 nanometer, 5 nanometers, and we also prepared 6 single element film, niobium, tantal, vanadium. I think this is thickness of 100 nanometers. And then you can see here, all material showed superconductivity because superlattice shows a bit lower superconductivity transfer temperature if you compare the bulk material. But anyway, we can get a sharp superconducting transition for superlattices. Then I asked Professor Ishizuka did the first principle calculation to check the band structure of this ABC superlattices. The model structure is here. Niobium 2 monolayer, vanadium 2 monolayer, and the tantal 2 monolayer times 5 periods. And this is the band structure calculation results. And if you zoom in the Fermi level here, then you see actually upspin band, downspin band is Rashba splitted. So we can see the Rashba spin band at Fermi level. And then with estimated coherence length by measuring the critical magnetic field. By using these formulation, we can estimate the coherence length of about 13 nanometers, which is much, much smaller than the film thickness. So up to now, we can say our film should be 3-dimensional Rashba superconductor. Okay. Then one day, my student, Ando, came to me and told me he got really strange experiment result. So actually he measured superconductor transition by injecting current, positive and negative, for his film under the application magnetic field, which is perpendicular to the measuring current. And what he showed me is this. So actually, he told me he got some fail, maybe. Why? Because he has the different critical current for different positive and negative current. It should not happen. But we check again and again, but finally, we have a conclusion that actually critical current itself depends on the measuring current direction under this magnetic field. So it means, so our film is superconductor in one direction for positive, but normal conductor in reverse direction. So it can be called superconducting diode. Then we try to check the dependence on magnetic field direction. So as you can see here, if you change the direction of field from up to down, then you see the polarity of superconducting diode effect change. So here you see some magnetic field here. It is the magnetic field of 0.02 Tesla. So you see the higher critical current for positive current. But if you reverse the magnetic field, now you have the higher critical current for negative direction. So the polarity of superconducting diode is reversed by changing the field. So we found polarity of superconducting diode can be switched by magnetic field. Then we demonstrated really superconducting diode. So for positive direction, here the zero resistance, but if you change the direction of magnetic field, then you can make superconductor to normal and so on and so on. So we can switch the polarity of superconducting diode effect. Okay. And what is the mechanism? And actually, I didn't know. But my naive explanation is the following. So because we have the superlattice without inversion symmetry, and actually, according to our calculation, it has a Rashba split, this kind of band. So if you inject a current, the electron should feel the effective magnetic field due to spin-orbit interaction. And this effective magnetic field depends on the direction of the electron flow. So here, I illustrate this explanation. Now we apply a magnetic field in this direction, and for the current towards rightward, then they feel the effective magnetic field by Rashba rightward. And this is parallel to the external field. But however, if we change the direction of the electron flow, then now you have the opposite directed effective magnetic field from Rashba. So this is anti-parallel to the external field. So this field reduces the effective total magnetic field. Then you can get the superconductivity in smaller total magnetic field. This is my naive explanation. But last year, I found, and I'm really shocked to see the very intuitive and very simple explanation by Yuan and Liang Fu. So this is a illustration by them. So it's just a Zeeman shift of Rashba split band. So now we have two Rashba split film circle, and if you apply magnetic field this direction, rightward, which is parallel to the electric current, then this magnetic field push the small film circle upward and larger one to downward. And if you apply magnetic field perpendicular to the current, then this magnetic field push the circles in a different way. So now you see the two circles is asymmetric with respect to the current direction. Then we can get the different superconducting critical current for positive and negative. This is a very simple explanation by them. And they noted, so this kind of signature, the Superconducting diode effect is a manifestation of helical superconductors. It means the Cooper pairs with a momentum. Okay. So if you see this figure, superconducting diode effect corresponds non-reciprocal superconducting current. Means under constant field, the superconductor has a different critical current for positive and negative direction. So this is superconducting diode effect, but in other words, it is non-reciprocal superconducting critical current. Then if you apply constant current, then we should have the different critical magnetic field for positive or negative field. So it can be said it is the non-reciprocal superconducting critical field, and we have checked it. So this experiment has been done by my former student, Yuta Miyasaka. Okay, now we applied constant current, and we applied magnetic field and change amplitude of magnetic field. So when we applied magnetic field parallel to the current, then we have no effect, right? Through line. And if we apply magnetic field perpendicular to the current, red one, actually we get different critical magnetic field for positive and negative direction. Oh, sorry, actually for simplicity, we plot the data for positive or negative in the same manner. Okay? And if we change the direction of current from positive to negative, then now you can see the polarity of this non-reciprocal mode field has been changed. So, in summary, we observed non-reciprocal superconducting critical current, which is superconducting diode effect, and also we observed non-reciprocal superconducting critical field, which is predicted by the theory. So now, let's make a diagram in HA plane. Okay, so from now on, I will show unpublished results. So this is a phase diagram by measuring many times for non-reciprocal critical current and non-reciprocal magnetic field. So critical current is a function of magnetic field and red circles. And critical magnetic field is a function of applied current, shown in black circles. So as you can see here, there's no difference between the magnetic field dependence of the critical current and the current dependence of the critical magnetic field. So we can say these non-reciprocal effects in superconductor has the same origin. Then we check the superconducting diode effect is a function of external field. Then we again found very strange effects. So here, delta JC defines as the difference of amplitude for positive current and negative. So this is the amplitude of SDE. So you see, not only we get a superconducting diode effect, and the polarity of SDE shows oscillation with magnetic field. And this data is get by my student, Ryo Kawarazaki, this guy. And he measured this effect in more details. So this is the same data that I have shown before. So he measures this effect as a function of temperature. So this is the data for temperature of 2K, means this line. Okay. So blue means positive STE, and red means negative STE. So it's a polarity change in STE. And as you can see here, the amplitude and period of the oscillation decrease with temperature, and the effect vanishes at Tc. Okay. And maybe Dido will present this data later, but I want to show you just comparison to experiment. So this experimental data, JC, and this is the theory calculation. So this is the JC as a function of external field. So you see both in experiment and theory, JC shows some infection here. And SDE appears around this infection. And Professor Dido also reproduced the polarity change in his calculation. And his theory predicts this is a crossover around power limiting field, and which is estimated to be about 6 Tesla for a sample, but which is much, much larger than the observation of several Tesla. Okay, and finally, I will discuss about the possible effect of vortex. Again, this is SE as a function of external field. In lower magnetic field, this peak, if we measure the resistivity as a function of electric current, so the sample shows zero resistance just before the transition. So we didn't see any signature of the vortex here. However, in the larger peak here, we measure the rho as a function of J, then we see notable resistance increase before the transition, indicating in this field there exists vortex motion. Okay? So I think we can say the lower field there's no effect of vortex, but in a higher field we have to consider the vortex motion in SDE effect. Okay, so last 10 minutes. Up to now, we need magnetic field to have SDE. The simple question is, can we have this effect in zero field, which is really preferable for application? So, as you know, we need magnetic field to break time reverse asymmetry to have SDE. So up to now, we break time reverse asymmetry by applying magnetic field. But the naive idea is to use ferromagnet. So we introduced cobalt layer in between vanadium here. Okay. So then here we have a ferromagnetic layer of cobalt. And we expect by using this Rashba superlattice with ferromagnet give us the superconducting diode effect in zero field. And also in that case, we got memory effect, which will open the possibility for some memory or some logic devices. Okay, then this is the structure of our film. So now we have 4.5, vanadium 4.5, cobalt 1.7, vanadium 4.5, times 4.5 times 20. And film structure design like this. And in this case, however, we get a 110 oriented film on MgO 100 substrate, which are a bit different from the superlattice without cobalt. Okay. Anyway, we checked the superconductivity and ferromagnetism. Further, you can see in this figure, the film shows the TC of 2.6 K. And also, film showed ferromagnetism, which is almost no change from 1.8 to 5K. So we got the coexistence of superconductivity and ferromagnetism. Then we checked the transport properties under magnetic field. So this is a plot of resistivity of our film is a function of external field. At the lower current, we see the gradual change, gradual transition from normal to superconductor to normal. But by increasing the measuring current to 18 kiloamps per square centimeters, you can see very sharp transition with hysteresis. So we can see here the effect of ferromagnetic cobalt in this hysteresis. Okay, it's a good sign. There we go to the SDE. So then we see the superconducting critical current by changing the direction of measuring current, positive and negative. So here you can see actually there's a difference in critical current for positive and negative current. Okay. So we get the magnetic hysteresis dependent superconducting diode effect. So there exists an effect of ferromagnetism in SDE. Then, so, okay, in this case, we applied magnetic field first positive 0.5 Tesla to saturate magnetization. And then we reduce the external field in this line. And at each point of field, we check the critical current for positive and negative electric current. And we see the JC is a function of external field like this. This is a downward sweep, the 0 Tesla. And then we reverse the direction of external field. Then we see the sudden increase in JC, which may be due to the cancellation of ferromagnet field and the external field. So we got a larger JC here. And then because of a change in the direction of ferromagnet, we got a reduction in JC and it's a trade. And then we get upward sweep like this. It's almost similar to the downward sweep. Then we check the SDE effect, which is the amplitude difference in positive JC and negative JC. So here you can see, actually, the SDE shows magnetic field dependence. So there exists a hysteresis effect of ferromagnet on SDE. But if you focus on the 0 Tesla in 0 field here, in every temperature, we don't have SDE in 0 field, which was a really hard report to me. Then, okay, I suggest to do minor loop experiment. So what a minor loop experiment? That is the point. First, we apply magnetic field positive 0.5 Tesla here to saturate magnetization. And then we decrease the magnetic field in this line. And then change the direction of into the negative field and go to the negative, but we return from minus 0.15, which is a smaller field than the initial field, and come back to the zero field. So now you can see the shift of hysteresis of JC into negative direction. And if you reverse the sweep direction, means from large negative value to small positive value, then you can shift this hysteresis into the reverse direction, in this case, positive. Then if you plot the SDE is a function of external field, then now we get SDE in zero field. Right? And positive SDE for from large positive field, and negative SDE in zero field from the sweep of large negative field. So we can get the SDE in zero field, which is controllable by the application of magnetic field, initial application of magnetic field. And we can demonstrate the switching of SDE in zero field by using this strategy. So now we got zero field SDE, and it showed non-volatile SDE. So I think this result opens the possibility of new device, for example, non-volatile memory or non-volatile logic devices. Okay, the last part is symmetry check. Now we got the effect with ferromagnetic cobalt in asymmetric structure. Means this film has polarity. So what's happened if we add here niobium instead of tantalum? Then now you see this 5 level has a symmetry. And then we lost SDE. But actually we need this kind of polar structure to have SDE. Okay, and this is symmetry check. So we just got SDE when we apply magnetic field perpendicular to the current, which is expected symmetry. And we don't have FCE for other symmetries, parallel B or parallel G or perpendicular field plane. Okay, so I think time is up. And this is my summary. Thank you very much for your attention. That's all.
Thank you very much for that really very nice talk. If there are any questions, I think the easiest is if an audience member would like to ask a question, please raise your hand on the participants list and I can call on you to unmute. We have a question from Nicola Paradiso.
Hi, thank you very much for the nice presentation. I have a question on the temperature dependence of your effect in your Nature paper. I see there that the effect tends to disappear at low, becomes weaker at low temperature, which is quite unusual because one would expect a saturation, and in the other work in the literature is observed. And actually in the last graph that you show, indeed one sees that at low temperature the effect is strong. Do you have an explanation why in that paper the effect was becoming weaker at low temperature?
Okay, maybe you see you say this result, and actually this result has get for the exactly the same device in Nature paper. So I think at that time our field amplitude of field sweep is not large, so we lost the effect around here. So we just see this effect close to the TC. So I think this is a correct result. Sorry.
Okay, thank you.
All right. Are there any other questions? We have one from Dr. Muhammad Shahbaz Anwar. Could you unmute? Yeah.
Thank you very much for a wonderful talk. My question is also related to the temperature. Do you think with the decrease in temperature and improvement of superconducting gap energy, and then the competition with Rashba energy, that it could be the reason of suppression of SDE at low temperature?
Yes, so yeah, I agree.
So then it means that the systems where spin orbit coupling is stronger might have a stronger effect at low temperature.
Yes, I think so. Yeah, I think the larger spin orbit coupling is the key to have the bigger effects. Yes.
Okay, thank you. Thank you very much.
I see also a question by Alex Cui.
Yes, thank you very much for your talk. I have a question about the zero field SDE effect. So how do you eliminate the possibility that the zero field SDE is due to trapped vortex flux inside your sample? Because if you have a trapped flux, it could also shift the center of the field dependence, so you might get like a SDE effect at zero field, but it's actually finite field.
But so even in this case, we start from large field where we should have the vortices, and we decrease among fields to 0. We should have the vortex here as well, but we don't have any SDE here. So the reason for this zero field SDE is different from the vortex effect, I think.
I see. So one of the previous sweep where you didn't see any SDE effect, what's the difference between these two sweeps? Oh, I see. So okay. Yeah.
Okay. There are a couple of questions in the chat. One of them from Vishnu Karki is asking, is there no SDE effect for the symmetric case only for the materials that have been chosen, or is it consistently that way for all symmetric materials combinations? Vishnu, please let me know if I've relayed your question correctly.
Okay, sorry. Look, honestly speaking, we didn't try to run many different combinations. So actually, we didn't see any effect for single niobium film. And then here we have the no effect in this asymmetric sample. Sorry, that's what I can say.
Yeah, I think that makes sense. And also a question from Yaojia Wang, saying that in the previous Nature paper, there's no cobalt layer, but the diode effect seems to depend on the sweeping direction of the field. And he asks, they ask, what is the origin of this?
I cannot understand the last example. So sorry, could you repeat the question again?
So I'm reading from the chat, and it says, in the previous paper, the diode effect seems dependent on the field sweeping direction. So whether the field is being swept up or down. And they're asking if there's any understanding.
Okay. Maybe you're talking about this result. So okay. For example, we measure the delta JC by sweeping, for example, in this direction, right? So because the polarity of the model field is different here and there, we should have the different polarity for SDE like this. So this effect should be symmetrical to the origin. And the important point is that we don't have any hysteresis here. But if we add cobalt, we have hysteresis SE. That's a difference.
Hello, thanks for your answer. I mean, in previous Nature paper, I saw there is figures, like when you sweep the field from negative to positive, and then from positive to negative, there is hysteresis of the delta I C versus B. It's not in this presentation, it's in the paper, so I'm confused about the hysteresis.
So sorry. I didn't remember the exact number in the Nature paper, but what's the question? And could you speak it more loudly?
Yes, if you could speak a little bit more clearly, I also had a hard time hearing. Yeah.
Okay, hello, can you hear me? Hello.
Yeah.
Sorry. Yeah, I mean, in previous work, there is no cobalt layer in between. And I saw there's one figure, but it's not in this presentation, like the delta IC versus B, it's dependent on the sweeping direction. For example, from negative to positive, it is like this, but from positive to negative, it's reversed. So I'm confused about this field sweeping dependence.
Oh, I'm so sorry. I remember the results. So
okay, maybe we can also discuss later. Yeah.
Sorry.
Yeah, we'll keep the question and can repeat, and we can go into it in the discussion section at the end of the day, perhaps. I don't see any other questions. I have maybe one quick inquiry, which is about how important is the dependence on the thickness of the layers inside the supercell, or the number of supercells? Do you have any insights on that?
Here, experimentally, we got this effect for thicker film. If we reduce the film 6 down to, for example, 10 nanometers, we lose the effect. It's an experimental fact, but I don't know the exact mechanism. And also it seems related to the quality of the film. So if the TC is small, then we experimentally observed a smaller effect. Sorry, what I can say.
Okay, thank you. And there is a raised hand. If your question is very quick, we can go to it. If not, perhaps you could pose it in the chat, and we'll have it ready for the discussion section.
I believe it's quick. For the minor hysteresis loop versus major hysteresis loop measurement, I didn't catch what's the difference in the magnetic state, or what do you expect is the difference in the magnetic state, which allows the superconducting diode effect for the minor hysteresis?
Okay. So minor hysteresis, I believe minor hysteresis loop give us a multi-domain state, and I believe it's a key to get SE in this case.
So why is that natural?
Pardon? Natural?
Well, why is it natural that
it's not natural. It's not natural.
I see.
Maybe I have 1 minute to explain. So my first naive idea to use exchange interaction between cobalt and electron Cougar pairs. In that case, we should have zero field SEE even after the saturation. But we could not get the effect, and we turned to the minor loop, and we got the results. So it means, so this ST effect in multi-domain structure should come from some stray field from the domain wall, or some effect of domain walls. I think so.
Thank you.
All right, let's all thank Professor Ono again. Thank you.